Hello, I would like to present our result about complexity of card-based protocols. And this is joint work with Michal, Koucký. So first, some example of a card-based protocol. We have two persons, Alice and Bob, and they want to know if they like each other or not. But they are quite shy, and if for example, Alice likes Bob and Bob does not like Alice, and Alice tells Bob that she likes him, and then he tells her that he does not like her, then Alice would be very embarrassed. So then Boer proposed a protocol how to solve this situation, and it works as follows. So both Alice and Bob has a bit 0, 1, and it represents if they like the other one, and they want to compute end of these bits, but they don't reveal their bit to the other party. So they represent their bit by 2 cards. So if, for example, Alice bit is 0, then she represents her bit by order club card and heart card, and in the other way, if she has 1 as her bit, then she represents it as heart card and club card. And in the same way, Bob represents his bit. And how the protocol works? So Alice put her cards here in this position in the reverse order, and Bob puts his card in the order he represents his bit. And on the last position, they put a club card. So if, for example, they both have 1s, then this order is club, heart, club, and note that the hearts are next to each other. But for example, if Bob has 0, then the hearts are separated by 1 club card. And this is also true if, for example, both have 0s. So these 2 hearts are separated by this card. So after that, they put all cards here. Then they random cut. What does it mean? They somehow split the cards into 2 piles and switch the piles. And they repeat this so many times that they don't know the order of the cards. However, the cyclic order by this operation is still the same. And so after this random cutting, they turn all cards. And if the hearts are separated by a club card, then they know that the end of their bits is 0. If they are next to each other, then they know that the end of their bits is 1. However, because of this shuffling, they don't know if this heart is, for example, from Alice or Bob. So this protocol is secure that they know the result, but they don't reveal their input. So we are interested in this problem that Alice and Bob want to compute some Boolean function, and Alice has the first half of the input, and Bob has the second half of the input, and they want to compute the function f on this input, but they don't want to reveal the input to the other party. So how to solve this problem? So we want to solve this with card protocols. So Alice and Bob represent the bits by cards. Again, one bit of each input is represented by two cards, and if the pair of the cards is ordered club card and the hard card, these two cards represent 0. If we switch the order, then the cards represent 1. And so they have some workspace between them, and where they work with the cards, and they may use some helping cards. And what's the elementary action they can perform? So first is move. So they can move the cards from their hand or from the helping cards, and they can turn cards, and they can shuffle cards. And at the end, there are some two cards which represents the output, so which represents the function fxy. And for example, if they are in this order, it means that the result of the function is 0. So to summarize the definition of the protocol, is that Alice and Bob can move cards, turn cards, and shuffle some cards. And output is represented by two cards. And the protocol should be secure. It means that each party not reveal any information about the input to the other party. And the complexity measure we are interested in is the number of cards and size of the workspace. So first, how to compute an arbitrary function with a card protocol. So basically, we need a secure protocol for AND and NOT, and then we can compute an arbitrary function. A protocol for NOT is easy because it suffices to switch two cards represent a bit. So if these two cards represent a bit B, then if we switch them, then they represent the negation of B. But the 5-card trick, which I showed you at the beginning of my presentation, cannot be used for AND because it does not produce two-card encoding of AND. So some previous results how to compute the functions. So first, Kripke and Kilian provide an AND protocol for computing an arbitrary function. This was improved by Nishida et al. That they proved that only 6 other helping cards can be are needed for computing an arbitrary function, and basically they evaluate the circuit computing the function, so it may lead to protocols of exponential length. And then it follows many other results about the improving AND protocol and XOR protocols and shuffling and so on. But as far as we know, there are no complexity results about card-based protocol. So we studied the complexity of such protocol and introduce a class of protocols which corresponds to the class NC1. So first, I will present some properties of protocols which we need for our result. So we say the protocol is oblivious if we have a counter which counts how many actions has already been made, and the next action, which will be performed by Alice and Bob, only depends on the counter and current state of the protocol. And we say the protocol is read-only if some card is moved from the position of Alice input to workspace, and for example, this card is club card, and later during the protocol, some card is again put on this position, then it has to be the club card. That basically the read-only protocol does not change the input of Alice and Bob during the computation. So now we can define some class of secure protocols as P, which we define is a class of functions computable by secure card-based protocols, such that the protocols are oblivious, read-only, and they have polynomial length, and also they use only S helping cards, and the workspace has size S, where S is some constant independent on the size of the input. And our main result is that this class SP is equal to the circuit class NC1, where NC1 is a class of function computable by circuits of logarithmic depth, polynomial size, and the circuits use only AND gates, OR gates, and negation gate. And we prove our result by using Barrington's theorem, which should prove the correspondence of the class NC1 and branching programs. So what is a branching program? So branching program is some graph where the vertices are split into layers, and each layer is labeled by some input variable. And in the first layer we have an initial vertex, and in the last layer there are two special vertices, accepting vertex and the rejecting vertex. And between two consecutive layers there are two matchings, one matching and zero matching, and we can see the matching also as a permutation between the vertices of the layers. Without the loss of generality, each such permutation corresponding to zero matching is identity, because we can reorder the vertices in the layers such that the zero matching looks like this. Now, how this branching program computes. So let's have an example of some input, and we start in the first layer in the initial vertex. So for example, the first layer is labeled by x2. We look at x2 and it's 0. So we choose zero matching and use the edge adjacent to the initial vertex from the zero matching, and use this edge and move to the second layer. And we have here a new active vertex. Now the label of the second layer is x3, so we look at x3, x1. So we use here the one matching and use again the adjacent edge to the x3, use this edge, and so on. And at the end, we end in the last layer. And we can end only in the accepting or rejecting vertex. And if we end with our computation in the accepting vertex, then we accept the input. And if we end in a rejecting vertex, then we reject the input. And we define class WBP as a class of functions which are computable by branching program, such that width of the branching program, which is the size of the layers, is W, and depth of the program, which is the number of the layers, is polynomial in N. And so I said that we prove our main result with using Barrington's theorem, which says that the class NC1 is equal for WBP for any fixed W larger than 5. So we prove two inclusions, that the class 5BP is in the class SP, and the class SP is in WBP for sufficiently large W. And with these two inclusions and with the Barrington's theorem, we prove the main result. So how we prove these inclusions? So first inclusion, let's have function from 5BP. It means that the function f is computable by a branching program with 5, and we represent the layer by card. So we start with 5 cards, and a heart represent the active vertex, and club represent the other vertices. And we want to track by the heart card where is the active vertex. So, for example, we have some input, and in this input x2 is 0. Then, according to this, we we do not want to change the order of the program cards and keep the heart at the top. And for example, if x3 is 1, then the branching program use some permutation, and here the heart card should move to this place. And then we continue in this representation, and at the end we end with representation of the last layer, and either the heart is on rejecting vertex or on accepting. So in this case, we take these two cards, they are as the representation of the output, and you can see that if heart is on the rejecting vertex, then these two cards representing 0. And if the heart card ends on the accepting vertex, then these two cards represent 1. So this is how this simulation is made. So we want a protocol for the following operation. So let's have 5 cards which represent the ith layer of the branching program, and let's have some card representing xj, which is a label of the ith layer. And if xj is 0, then we don't want to change the order of these 5 cards. And if xj is 1, then we want to change the order of these 5 cards by some permutation pi, which is given by the branching program. So we decompose this permutation to transpositions and apply sequentially each transposition to those 5 cards. So the basic operation is to apply some transposition if xj is 1. So in this example, if xj is 1, we want to switch the second and fourth card. And if xj is 0, then we don't want to switch those cards. So if we apply this operation for each transposition, we apply the permutation pi on those 5 cards if and only if xj is 1. So how we prove the other inclusion, that the class SP is can be simulated by branching programs. So if the function is in SP, then we call that, then there is some card-based protocol where Alice and Bob use at most S helping cards, and the workspace has at most S positions. And S is some constant. So know that here we can have at most 5 to 2s states, because at each position it can be either empty, or there can be club card or hard card, and the card can be face down or face up. So each position can be at most 5 states, and we have S position in the deck and S position in the workspace. So we have at most 2S positions. So here we have at most 5 to 2S states, and we use this to design a branching program with 5 to 2S, where each vertex in each layer represent some state of the workspace and the deck of helping cards. So we have some other results. So we prove that if the protocol can use logarithmically many helping cards and logarithmically sized working space, then this protocol is equals to non-uniform block space computation, which is equal to poly-sized branching programs. And the proof of this is basically the same as the proof I was just talking about. The next result is that we can simulate the Turing machine by protocols, and the number of helping cards and the size of the workspace basically correspond to the space to use by the Turing machine we are simulating. And also we are interested in read-write protocols. So those are protocols which can change their input during the computation. We were interested if those read-write protocols are more powerful than read-only ones, and we proved that if so, then we would be able to separate the block space from NC1, and also by technique of catalytic computation, we proved that the read-write protocols can compute the problem connectivity, which is complete problem for non-deterministic block space. So from these two results, we conclude that probably the read-write protocols are more powerful than read-only ones. We are also interested in more efficient encodings. So the first one is one-card encoding, where the input is encoded by 1 card per bit. So the 0 is encoded by club card, 1 is encoded by hard card. But the computation is done in a 2-card encoding, and we are able to adapt the read-only protocols for the 1-card encoding. We provide a protocol for copying a bit encoded by 1 card to the 2-card encoding, and it is done by slight changes of known protocols from the previous works, and then we just use read-only protocols for the 2-card encoding. And we also have similar results for read-write protocols, but here we need to be very careful about the security. And the last encoding we considered is one of 2-card encoding. So in 1-card encoding, we use 2 N cards to encode 2 N-bit input. But overall, we still need 4 N cards for representing any input. So this issue can be handled by one of 2-card encoding. So 0 is represented by a club card and empty space, or by empty space and hard card. And 1 can be encoded by empty space and club card and hard card and empty space. Note that this is just like a 2-card encoding, but one of the pair is remain. And how the Bob and Alice commit their input. So let's have representation by 2 cards of the input, and each Alice and Bob pick random n-half of their bits. So, for example, they pick these two bits, and in this selected bit, they remove hard card, and in the remaining they remove a club card. So, probability of removing the left card is 1/2 exactly. So, from the empty position, no information is leaked, and actually they use exactly n-half heart and n-half club to represent their n-bit input. So for read-only protocol, we can use the same technique as for the one-card encoding, and we can conclude that function from NC1 can be computed by a second card protocol using only 2n plus some constant card. And note that 2n is actually the size of the input. But for read-write protocols, we do not know how to use the technique from the one-card encoding. So we don't know how to design a second protocol for read-write operation in the one of two-card encoding. The problem is with the empty position, that they may leak some information. So to summarize our results is that we characterize the class NC1 by card protocols, and by one of two card encoding, the protocol needs only 2n plus 01 cards. And if we allow logarithmically many helping cards and logarithmically size of the workspace, then the protocols can compute functions from non-uniform workspace. We can simulate the Turing machines where the number of helping cards and the workspace corresponds to the space of the Turing machine. And probably read-write protocols are more powerful than read-only protocols. So thank you for your attention.